In this video, we will be reviewing some functional groups that make up organic molecules. It is sometimes nice to see and know some of the names of these functional groups before we actually discuss them in detail. So this is a review. If we look at this big molecule on this slide, you can see there's sulfur in this molecule, there's oxygen, there's nitrogen, there's triple bonds, there's double bonds, there's aromatic rings. Each of these is a functional group. So in this presentation, we'll talk about hydrocarbons, molecules that just have hydrogen and carbon, oxygen-containing molecules, nitrogen-containing molecules, and sulfur-containing molecules. Molecules are often classified by their functional groups. In many ways, organic chemistry is the study of reactions and interconversions of functional groups on molecules. So to convert, for example, an alcohol over to a thiol, that would be organic chemistry. A molecule's functional groups dictate its physical properties like melting point, boiling point, density. It also dictates its chemical reactivity. All the different electron environments around those functional groups dictate where chemistry will happen. And it will also dictate how we name organic molecules, the nomenclature. This big list over here to our right is just a list of many popular or common functional groups, and we're going to look at a limited number of these this semester, but we're also going to introduce some that we'll talk about in more detail next semester because we'll still see them as minor components this semester. We're going to be talking about three broad classes of organic molecules in Chem321. Hydrocarbons, which are organic molecules that contain just carbon and hydrogen. We're then going to add some oxygen to those hydrocarbons, add some nitrogen to those hydrocarbons, and we'll also add a little sulfur. So we're going to be talking about alkanes, cycloalkanes, alkenes, alkynes, aromatics, alkyl halides, alcohols, and thiols this semester. Next semester, we're going to be talking about a number of other functional groups. However, we will see all these functional groups this semester because we're going to be talking about the chemistry of alcohols and how we make them into aldehydes. So we need to know these functional groups this semester also. And when you take biochemistry, which I hope you do, all these functional groups are part of carbohydrates, lipids, proteins, enzymes, vitamins, and nucleic acids. Let's take a look at hydrocarbons. Again, compounds composed entirely of carbon and hydrogen. We call these alkanes if they contain just single bonds between all the carbons. These carbons can be arranged as a linear molecule where all the carbons are connected in a line. For example, this is butane here. It contains 4 carbons. Alkanes can also exist as branched molecules where I have a branch here. I have 3 in a row, then 1 branching off the center. This is called isobutane, or with the IUPAC nomenclature, that would be 2-methylpropane. We can also have cyclic hydrocarbons where we have the carbons bonded together to form a ring. This is an example of cyclobutane. Alkanes are named based on the total number of carbons, the branching patterns, and any cyclic structures that are present. And we will discuss these in detail in future chapters. Let's look at a short list of linear alkanes. If I have 1 carbon, we call that methane, CH4. 2 carbons in a row, that would be ethane. 3 carbons, propane. 4 carbons, butane. 5 carbons, pentane. 6 carbons, hexane. 7 carbons heptane, 8 carbons octane, 9 carbons nonane, and 10 carbons decane. You can see once we get up to 5, we follow the Greek and Latin for actually naming these compounds depending on how many carbons there are in a row. These first 4, methane, ethane, propane, and butane, are historical names. You can see here is the condensed formula for all those, and here is the line angle formula for all those hydrocarbons. We also can have cycloalkanes, where I have, in this case, 5 carbons in a ring structure, or drawn with just the line angle. It has 5 carbons, so it's going to be a pentane, but we add the prefix cyclo to it to identify it and differentiate it from the linear chain hydrocarbons. This would be cyclopentane. This molecule over here, let's see, it has 6 carbons in a ring, so it would be cyclohexane. Branched hydrocarbons are hydrocarbons that have not only a linear row of carbons connected together, but somewhere they branch with another carbon. For example, I have 1, 2, 3, 4 carbons in a row here. That would be 4 carbons would be a butane, and I have 1 carbon sticking off that row, and that's a methyl group, and so this would be 2-methylbutane. Here's another example of a branched alkane. I have 1, 2, 3, 4 carbons in a row again, so that's a butane. And I have 2 methyl groups now, 1 sticking out of the board, 1 sticking into the board. At the number 2 position on this hydrocarbon, this would be a dimethylbutane. The longest carbon chain is often called the parent chain. So my longest chain here is 4 carbons, we call it butane. My longest carbon chain here is 4 carbons, we call it butane. All the other chains we call substituents. So this methyl group up here is a substituent, and these 2 methyl groups are substituents off the parent chain. Often we represent a generic substituent as an R group. For example, this molecule here, this group down here is my substituent because my longest carbon chain is 6 carbons here. So this would be a cyclohexane, and a substituent would be an isopropyl group. Sometimes we represent that again as just an R. This R just means there's something else hanging off of my parent chain. Some common substituents, or alkyl groups, are a methyl group, ethyl, propyl, and butyl. Notice that these words take their base from the methane, ethane, propane, and butane because they're listed by the number of carbons in that substituent. This squiggly line here indicates the parent chain, which is a much bigger part of the molecule. Alkenes are hydrocarbons that contain 1 or more double bonds, and we're going to discuss that in a later chapter. The double bond is a functional group, and this functional group is very reactive. If I have 2 carbons, 1, 2, we call this ethene, eth meaning 2. If I have 3 carbons and I have a double bond somewhere, this is a propene. If I have 4 carbons, this is a butene. 5 carbons is a pentene, and 5 carbons is also a pentene, but notice these two, the double bond is in a different place. So we identify and distinguish these 2 molecules by putting a 1 out here in front of the pentene to identify that the double bond started at carbon number 1. In this last molecule, I go 1, 2, the double bond started at carbon number 2. We can also have cycloalkenes, and they can exist as either a cis isomer, which we'll talk about again in a later chapter, or a trans isomer, but I have to have at least 8 carbons to have a trans isomer. So here I have 5 carbons, I have a double bond, that's a pentene, and it's a cyclopentene. Here are 6 carbons, and I have a double bond, this is a cyclohexene. Here I have 10 carbons and a double bond, so it's a cyclodecene. However, you can see that the orientation of this double bond, here we sort of have the zigzag structure here. That would be trans stereoisomer. And here we have this sort of folded structure. That would be the cis stereoisomer. Alkenes are hydrocarbons that contain triple bonds. Here is a 2-carbon alkene. That would be ethine. This has a 3-carbon triple molecule with a triple bond. This is a propyne. And here is one with 4 carbons, and it has, so it's going to be a butyne, and the triple bond starts at carbon number 2, so we throw a 2 out in front of that. We can also have cyclic alkynes, or a cycloalkyne, but I need to have more than 8 carbons in that cyclic ring, or there's just too much strain because it's bent. This one would be, let's see, I count carbons, I see there's 8 carbons in here, so that would be an octyne, and it's cyclic, so it's a cyclooctyne. This molecule is called benzene. This is benzene with a substituent off of it, and it's 2 carbons, so it's an ethylbenzene. Here is a benzene with a generic alkyl group on it, R, so it's an alkyl benzene. I can also have pentenes where AR is a substituent, but it's just called an aromatic. So I can also have a generic aromatic substituent, or sometimes we even call that aromatic substituent a phenyl. So this AR means benzene, this pH means benzene. Alkyl halides are hydrocarbons that contain a halogen, fluorine, chlorine, bromine, or iodine. Typically the nomenclature is as a substituent prefix, so that prefix for fluorine would be fluoro, prefix for chlorine would be chloro, bromo for bromine, and iodo for iodine. Generically, we often represent a halogen as an X in a molecule. That means it can either be fluorine, chlorine, bromine, or iodine. It has the same reactivity. Here is a molecule with both chlorine and bromine. Here is a molecule with chlorine and bromine. Here is a molecule with fluorine. That's a 1-fluoropentane. Here's a 2-bromopentane, and here's a 3-iodopentane. Again, noticing that my parent chain is always listed as my longest continuous carbon chain. In this case, they're linear, so it's a pentane, pentane, and a pentane. Alcohols are hydrocarbons that contain a hydroxyl group on them, or OH. Nomenclature-wise, we add the suffix -ol to the end. So generically, I have a generic hydrocarbon with an OH, that's an alcohol. This is methanol. I have 1 carbon with an OH on it. Oftentimes, historically, we call this methyl alcohol, or MEOH. If I have 2 carbons, we call it ethanol, and I have another historical common name, ethyl alcohol, or ETOH. I can also have more complex alcohols. I count the number of carbons here. That's 3 carbons. That would be propane. And when I add the OH to that, I call it propanol. Here is another propanol, but my OH is coming off carbon number 2 now. 1, 2. So we call this 2-propanol. For both of these molecules on the bottom here, we also have common names, N-propyl alcohol and isopropyl alcohol. You might recognize isopropyl alcohol. That is also called rubbing alcohol, and it's the alcohol we use to disinfect your arm before you get a shot. Thiols are hydrocarbons that contain a sulfanyl group or a sulfur hydrogen, much similar in reactivity and nomenclature to alcohols. Nomenclature-wise, this is our thiol suffix. Thiols are sometimes referred to as mercaptans. That's an old historical name, specifically related to the scent of skunks. So thiols typically smell bad. So here's a generic equivalent. I have a generic R group with an SH attached to it. It's a thiol. Here's a 2-carbon thiol, ethane thiol. Here's a 5-carbon thiol with a substituent SH and a substituent CH3. Here's an aromatic thiol, benzene thiol. Ethers are a functional group where I have an oxygen with 2 alkyl groups bonded to that oxygen. We often identify the alkyl groups and then follow that by the word ether for nomenclature. So generically, I have an R group attached to an oxygen with another R group attached to it. Here I have a methyl group and a methyl group, so we call this dimethyl ether. Here I have an ethyl group and an ethyl group. We call this diethyl ether. Here is an example of ether that also has a double bond in it. This has a common name of a furan. Here is another ether with a methyl group and this more complex substituent out here, which is called a T-butyl group. A carbonyl group is a carbon with a double bond to oxygen. That is considered a functional group. Ketones are 2 alkyl groups bonded to that carbonyl group. So my carbonyl group again is the carbon double bond oxygen. I have 1 generic alkyl group attached to it and a second generic alkyl group attached to it. We name these by finding the longest continuous carbon chain. That's going to be 3 carbons, so it's propane. I change the E to an one. This is actually a ketone, so this is 2-propanone. This would be 2-butanone because there's 4 carbons now here. And here is cyclohexanone. Aldehydes have an alkyl group attached to it and 1 hydrogen bonded to that carbonyl group. So here's my carbonyl group, again, carbon double bond oxygen. I have 1 alkyl group and 1 hydrogen attached to it. Notice it looks very similar to a ketone. It just happens to be at the end of a hydrocarbon chain. So here's 2 carbons, that's ethanal. We name aldehydes as als. Here's 3 carbons, propanal. Here's 4 carbons, butanal. Also notice there are some common names to it. Acetaldehyde, propionaldehyde, and butyraldehyde were named back in the 1800s, and those nomenclature is still sticking around today. Carboxylic acids also contain a carbonyl group, but they also contain a hydroxyl group attached to that carbonyl group, and the end of the name is usually oic acid. So this is a 1-carbon carboxylic acid. We call it methanoic acid, or the common name is formic acid. Here is a 2-carbon carboxylic acid, ethane, ethanoic acid, common name acetic acid. Acetic acid is just vinegar. Propanoic acid has 3 carbons in a line here. This is propionic acid, and butanoic acid or butyric acid, 4 carbon systems. Okay. Acidity from carboxylics results from the resonance stabilization of the carboxylate anion. So if I take any carboxylic acid and I throw it in water, there's a tendency for that hydrogen to be pulled off by the water because it's a little bit acidic. And once I draw my carboxylate anion, I notice that I can draw a resonance structure again, and that implies stability. If I have a stable anion, that implies that this is a moderately good acid. We also have some derivatives of carboxylic acids. So my carboxylic acid, I have a carbonyl group with an OH attached to it. If I have a carbonyl group with a chlorine attached to it, we call that an acid chloride. If I have a carbonyl group with an OR attached to it, we call that an ester. The reason we call these derivatives of carboxylic acids is because in order to make an acid chloride, I start with a carboxylic acid. If I want to make esters, I start with a carboxylic acid and do some chemistry to them. Here's some examples of Carboxylic acids again, acetic acid, acetyl chloride, and ethyl acetate. Amines are hydrocarbons that contain nitrogen. Okay? The simplest one is ammonia. Generally, these are considered basic compounds, mean they're alkaline in nature. Simple amines are named by naming the alkyl group followed by the word amine. So for example, generically, I have an R group with an NH2 group on it, or I could have an R group with a nitrogen and another R group, or I could have 3 R groups attached to that nitrogen. This is a primary amine, a secondary amine, and a tertiary amine. So naming it, I call this methylamine. This one I call ethylmethylamine, and this one I call triethylamine. Those are amines. I can also have amides. If I look at an amide, I still see here a carbonyl group, a carbon double bond oxygen, but in this case I have what looks like an amine looking structure here. This whole group together is called an amide. So generically I can also have primary amides. I'm looking at what's attached to that nitrogen. I only have 1 carbon attached to it. Secondary amides or tertiary amides. This is common name acetamide. This is an N-methyl acetamide, and here is N,N-dimethylbenzamide. Nitriles are also nitrogen-containing hydrocarbons, but now I have a carbon triple bond nitrogen. So that generically, this is a nitrile. Here is acetonitrile, here is propionitrile, and here is benzonitrile. Each of these has a carbon nitrogen with a triple bond on it. Let's do a little bit of functional group analysis and practice exercise. I'm going to get rid of my cursor here. Let's first highlight all the different functional groups and then look at them. Let's first look at the red functional group here and try to identify it. That's an OH group. That's just an alcohol. If I look at the blue 6-membered ring, that's an aromatic functional group. If I look at the NH2 in green, that's an amine. If I now look at the carbonyl group with a nitrogen-containing compound to it, I need to remember that that whole thing is a functional group. It's not a carbonyl with a nitrogen. It is an amide. I can see there are 2 of them here. If I look at the sulfur in purple, that is actually a thioether, which we do not discuss this semester. And finally, the COOH in brown there is a carboxylic acid, abbreviated. If I come over here to codeine and highlight some of the functional groups in color, and let's start up here at the top with this sort of purple fuchsia functional group here. Those are going to be ethers. Both of them are oxygen with carbons on both sides. There's a carbon, oxygen, carbon. If I look at the blue here, that's going to be another aromatic. Coming down here to the green, that's actually going to be a tertiary amine. I have a nitrogen with a carbon, carbon, and carbon. If I come down here to the pink color, that's just an alkene, a double bond. And finally, the hydroxyl group down here at the lower left-hand side, that's going to be an alcohol. The molecule down here at the bottom is very complex, and there's a lot of functional groups on that. Let's take a look at some of those. So if I look at the blue, I see that, let's first here, there's a blue down here. That's actually a simple way of writing an aromatic benzene. I also have some acronyms here. AC stands for acetate, and so I have a carbonyl with 1 methyl. I have a 2-methyl acetate. So again, let's start at the beginning there. All the ones in blue, 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 and this benzene down here are aromatic systems. The one here in yellow, I have a carbonyl group with a nitrogen attached to it. That's my amide again. I work my way over here to the red parts. I have alcohol here, and I have an alcohol here. The greens are going to be esters. That's a carbonyl group with an O carbon onto it. Here is another ester, and here's another ester, recognizing again that I have an oxygen here with this acetate group sticking up here. This dark green here, let's go to the fuchsia again. That's an alkene. My dark green is going to be a ketone because it's a carbonyl group sort of in the middle of a molecule. I have an R group here and an R group here, meaning a carbon and a carbon. I then have my ether down here, and I have another ether here. It happens that this ether is to a benzene ring. Functional group review. Oh, and I have a cyclic compound. This one is actually cyclic. This molecule is actually the same molecule as we showed on the second slide. And you can see there are all these different functional groups in here. This is an antibiotic, calichiamycin. And from this point forward in this class, we're going to be talking about the organic chemistry and how we can look at the reactivity, interconversion, synthesis, and nomenclature of all the functional groups that we just talked about. Over here on the right-hand side is a synthetic methodology for actually producing that antibiotic. With starting materials, reacting them together, I can change functional groups to actually put them all together to make that molecule. Let's name this molecule. It's got a gigantic name. This name here, we might be able to even name this molecule once we're done with first semester of organic chemistry and the second semester of organic chemistry. You can see the common name is a lot easier to write down anyway. That's the end of the functional group chapter. We're now going to go on to chapter 2 and study acids and bases of organic molecules.